Good afternoon, everyone. Welcome to the video lecture of Control System Engineering, module number 3, Transient Response Specification. Okay. Now, in the previous video lecture, okay, yesterday also we have seen something about the transient response specification. Okay, I've just gone through the basic requirement, okay, or the basic response, okay, or simply you can call it as the basic specifications which are required for the transient analysis. Okay, so therefore today we will go in detail and we'll try to derive the how the this particular response specifications will meet the requirement of the transient response analysis. Okay, so here in the transient response analysis specification, okay, so in my previous video lecture, okay, so I have considered one signal, okay, which is starting at point 0 and it will reach to its maximum 100%. Okay, not only with the 100%, but it is reaching something beyond the 100%, and that particular point is known as the overshoot, denoted by MP. Okay, so following definitions are being studied in the previous video lecture with some tolerance band of plus or minus 2%. So therefore, here there are various definitions we have defined in the previous video lecture, like TD, that is the delay time. Okay, then we have rise time, okay, peak time, overshoot time, okay, and then settling time. So these are the 5 very important definitions we have discussed in the previous video lecture. Okay, but now in today's video lecture we will try to derive, okay, we will try to derive and get the this particular derivations. Okay, so these derivations, whatever we have seen in the definitions we have seen in the video lecture, today we will try to derive and see what answers we will get. Okay, so let us start with the very first derivation, very important derivation. Okay, and the very important thing here is the derivations which we consider in this video lecture will be of second order. Okay, so because the transient response is analyzed for the second order underdamped signal, okay, so all the derivations which we derive will be with respect to second order underdamped. Okay, so let us consider the very first derivation is for peak time represented by TP. Okay, so TP is nothing but your peak time denoted by the letter TP, and sometimes the question will be asked about how derive the equation for the peak time TP for second order underdamped system. Okay, so let us consider one the output C of T, or the output response of the system. Okay, now always remember, now the derivation whatever we do here, it will be all with respect to transient analysis. Okay, so therefore let us consider the output C of T here. Okay, it is given by 1 minus exponential e raised to, or we can call it as exponential raised to minus zeta into omega n multiplied by time t. Okay, you can see here multiplied by time t divided by root of 1 minus zeta square multiplied by sine omega d plus theta. Okay, so this is the equation, this is the transient response of second order underdamped system. Okay, now what is the assumption what we have made, that the system which we have taken for the analysis is the second order with respect to time transient response, but it is underdamped. Okay, we are not considering the overdamped, we are considering only the underdamped condition here. Okay, so therefore once if I consider this time t, the transient response that is represented by C of t, and always remember this C of t is nothing but your output. Okay, C of t is nothing but your output response of the system. Okay, now the angle theta, okay, so this angle theta is denoted by the tan inverse of root of 1 minus zeta square divided by zeta. Okay, so this is the formula for theta. Even if you substitute the value of theta in this equation, you will find the actual value of theta, but when it is measured when it is measured or in that particular transient response graph. Okay, now what condition we will consider here is, let the time t is equal to tp. Okay, if t is equal to tp, for example, if you're starting at point t t is equal to 0, okay, t is equal to 1, t is equal to 2, t is equal to 3. Okay, sometimes that signal which you are getting at the output of the system once each reaches to point TP. Okay, at point TP, I will just show you the graph which we have seen in the yesterday. Okay, this you can see. Okay, this is the point TP. This duration is my TP duration. It starts from 0 and it is reaching to its maximum point is TP. Okay, this is the what the assumption which we are going to consider here now for this particular derivation. Okay, then C of t will achieve its maxima. Okay, its maxima in the sense maximum value at point TP only. It is receiving its 100%. Sometimes it will go beyond the 100% value. Okay, so therefore first we have considered the output signal, define the angle theta, then we will consider the one assumption or one point here that at t it is equal to TP. Okay, and what is happening at point TP? The value of C of t is reaching to its maximum value. Okay, the value whatever we have mentioned here, it is reaching its maximum value. Now let us consider one theorem here, that is it is maxima theorem. Okay, how to define the maximum theorem is it is differentiating or d by dt of C of t. Okay, differentiate the output signal C of t with respect to t which is equal to TP, then which is equal to 0. It is just simply like at t is equal to TP which is equated to 0. Okay, so according to the maximum theorem or maxima theorem, d by dt of C of t at t is equal to TP is equal to 0. So let us differentiate the C of t with respect to t, because this is my C of t. Now you need to differentiate this output equation with respect to t. Okay, so once you differentiate with respect to t, the equation what we get here is minus of e raised to minus zeta omega n into t. Okay, my bracket minus zeta into omega n sine omega dt plus theta. Okay, plus theta. You can see this equation and this equation divided by root of 1 minus zeta. Okay, divided by root of 1 minus zeta, whatever the value we got. Okay, minus e raised to minus zeta into omega n into t divided by root of 1 plus zeta square multiplied by omega d into differentiation of sine is nothing but cos. This part. Okay, so differentiation of sine is nothing but it's the cos omega d into t plus theta is equal to 0. What we have done is we have differentiated the output signal C of t with respect to 0, and then after differentiating we will equate it to